Hi everyone, this is a lesson about the definite integral. So the definite integral is right here. This sign is the integral sign, and this integral is definite because it has numbers a and b on the top and the bottom, right? That's what makes this integral definite. We're going to also have just the integral with no numbers, and this is going to be the indefinite integral. And we'll get to that a couple lessons from now. But the topic of today's lesson is this definite integral, and we have just learned that the definite integral is the limit of a Riemann sum. So when you make a Riemann sum to estimate area, we're doing height times width of all these rectangles. There are n rectangles. And then if we take a limit as n, the number of rectangles goes to infinity, then we get the exact area, right? So that's what the definite integral is, and this limit is so important, and that's why it has its own special name, which is the definite integral. So we want to remember that the Riemann sum is approximate area, and the definite integral is exact area. The definite integral is exact, okay, area. Okay, so this limit, if you remember, we did this problem in class where we actually did the algebra to find the limit of the Riemann sums to estimate, you know, the area under the graph of x squared going from 0 to 1, right? So you might remember we wrote that Riemann sum and we took the limit and we used the series, quadratic series formula to simplify it, and it was a bunch of algebra, and we came out with an answer of 1/3, right? So we know this exact area here is 1/3. Now, the limit, we were able to find that. You know, we can say now that the integral from 0 to 1 of the function x squared dx is equal to 1/3 because we figured that out, right? However, sometimes the limit doesn't exist. It may or may not exist. So that's why we say here, if this limit exists, then the function is called integrable. We say the function can be integrated, it is integrable. And functions that are continuous on the interval, on the closed interval, I should say, on the closed interval a, b, or if they have a finite number of jump discontinuities, those type of functions will be integrable in general. Okay. Calculating a definite integral is called integrating, just like taking a derivative is called differentiating, right? So integrating is the verb, and the definite integral, I'll change this word, is always an area, is always a number. It represents an exact area, and so you saw it right here. This definite integral came out to be a number because it represents an exact area. Okay, so I can actually just rewrite that here so I can make some statements about that. This definite integral we said from 0 to 1 of x squared dx. What does this mean? This means the exact area under the graph of x squared going from 0 to 1. There are some words we use for these pieces of the integral. This is going to be the function. We call it the integrand. It's going to be different functions for different integrals. That's the integrand. We already said this symbol is called the integral symbol. The numbers at the top and the bottom. The number on the bottom is called the lower limit, and the number on the top is called the upper limit of integration. Integration kind of has a direction, right? We say that we are integrating from 0 to 1. We go from the lower limit to the upper limit. We're integrating from 0 to 1. And we just said, by the way, that this whole answer is 1/3, right? So the answer to a definite integral is always a number. This x, this variable, and this x always have to match, and that variable, whatever it is called the variable of integration. Okay, so the variable of integration does not change the number, right? What do I mean by that? By that I mean that this right here, integral of x squared dx from 0 to 1, means that if I have a graph of x squared and I sit there and calculate the exact area from 0 to 1. This exact area is equal to 1/3, right? Well, I can say the same thing by saying integral from 0 to 1, t squared dt is equal to 1/3, right? See how the number didn't change? It's just that my graph is now t and t squared, right? But clearly the area from 0 to 1 didn't change because I called my graph by a different variable. Integral from 0 to 1 of theta squared d theta will also be equal to 1/3, right? So the variable of integration does not change the answer to a definite integral. Okay, we've been doing a lot of Riemann sums in the last couple lessons, but they were all usually, I think, positive functions, right? But now we're going to expand the idea of the Riemann sum and of the integral to functions that are both positive and negative over the interval AB. And therefore, because the function can be positive or negative, we're going to get an answer which represents a net area. Okay, so the integral from a to b of the function, this means we're finding the area of the function from a to b, right? And this is going to represent the net area. So areas that are positive are going to count as positive areas. Areas that are negative are going to count as negative areas. And we're going to add and subtract all of that to get an answer, right? So really, the answer is going to come out to be the area above the x-axis minus the area below the x-axis, right? Because areas below are going to be negative, areas above are going to be positive. If we're moving from, this is assuming my integral was moving from left to right. In other words, you know, a is less than b, right? So if I'm moving from like 1 to 10 this way, right, then areas above the axis are positive, areas below the axis are negative. Let's show another example here of an integral. I'm going to take the sine function. That's not a very good picture. The sine function is should look more symmetric, right? It's exactly the same wave just going up and down, right? Let me go for 3 cycles from 0, well, sorry, for 1.5 cycles from 0 to 3 pi, right? So if I were to say the integral of the sine function, this is the sine wave here, from 0 to pi, it so happens, you don't know this yet, but I'm just telling you that this area right here works out to be 2, right? And because everything is symmetric, these shapes also have area 2. But if we're going to do an integral, then the integral from 0 to pi would be 2. The integral from 0 to 2 pi of sine x dx would be 0, because it would be 2 minus 2, or 0, okay? The integral from 0 to 3 pi of sine x dx would be 2 again, right? So that's the idea here with how we use net area, how the integral gives us net area. What else? I wanted to also mention that this is kind of similar, the net area, to displacement in physics, right? And then I want to talk about total area, which is similar to total distance traveled in physics. So if you're looking at total area on this graph here, or on any graph, we would have to do the integral from a to b of the absolute value of f of x dx, right? Which basically means, like on this sine graph, that would mean that we just flipped the negative piece positive, because that's what an absolute value does to a graph. It just takes all the negatives and flips them back over the x-axis so they become positive. So now this would be my situation, and if I were to do the integral of the absolute value of sine x dx from 0 to 3 pi, that would have to be 6, okay? And I could write that as the integral from 0 to pi of sine x dx, because for that first stretch, the sine function is positive, so its absolute value is itself. When I'm on this stretch right here, absolute value of sine x would have to be negative sine x, right? Here's my absolute value, and here is my actual sine, right? So I had to put in a negative sign because of the sign being negative from pi to 2 pi. So I'd have to say minus the integral from pi to 2 pi of sine x dx plus the integral of 2 pi to 3 pi sine x dx, right? That's how you would kind of break up this integral if you wanted to write it out in terms of each of the pieces, and this total would be equal to 2 minus negative 2 plus 2, and the total would be 6, as we expected. Okay, so now we're going to look at some properties of integrals, the properties of definite integrals. The properties are down here, and I'm just going to refer to them as I do examples that relate to each property. So here, this first property first example here is an example of the property which I call box in the table, because we are integrating this function. This is a function, f of x is equal to 5. Not just a number, but we're thinking of it as a function. Here's a 5. Flat function at 5 just sits there forever, and we're integrating it from negative 10 to 10, and that simply means we're finding this area from negative 10 all the way to 10. And you can see that this integral can be done just with a geometric shape. This is a rectangle. It's a box. Its width is 20 and its height is 5, right? So here's my width and here's my height, and I have a box. So I can just find the area of this box. That's why I called it the box property, and this equals 100. If the box had been the integral of negative 5 dx, right, from negative 10 to 10, then first let me show you this constant property. Constant multiple property says that if you have a constant number inside the integral, you can pull it out through the integral if there's a constant multiplying f, right? So here I can think of it as this is a negative 1 multiplying the 5. So the negative can come out, and then I'm doing the same integral that I had before, right? Geometrically, what I'm really doing is calculating the area of, let's just draw it like this. This one here would be a box where the function is down there, and we're going again from negative 10 to 10. So again, we have an area of the just the shape has an area of 100, but since it's an integral, this is going to come out to be negative 100. Okay, then we have this guy. So here, this is an example of the sum and difference property, which is down here. So this is our sum and difference property, which says that if the integrand is a sum and difference of functions, we can break up our integral, right? Notice the limits are staying the same, right? But we can break up the integrand into pieces. So here I can think of this as the integral from 0 to 3 of x dx minus, again, I'm kind of using the constant multiple property as well, the integral from 0 to 3 of 1 dx, or of just dx. When you see this, right, we're really just saying it's 1 times dx, okay? So now the integral from 0 to 3 of x dx, we're going to think of that as a shape, right? It's a y equals x function here. Y is equal to x. And I'm going from 0 to 3. So if I'm at x is equal to 3, then this point here is 3, 3. And I have this little triangle. This is the area that that definite integral represents. And that's going to be 1/2 of, so we're calculating area, 1/2 of 3 times 3, minus this piece is a flat line, right? That's my flat line at y equals 1, and I'm calculating area from 0 to 3. And so here, this is a box, and the box is 3 wide and 1 high, so minus 3. So 9/2 minus 3, which is 6/2, gives me an answer of 3/2. So this integral, remember an integral is always a number, and that one is 3/2. This right here is the equation of a circle. This is the top of a circle. Circle equation is x squared plus y squared equals r squared. So y equals plus or minus the square root of r squared minus x squared, right? That would give you the whole circle of radius r centered at the origin. If you're only seeing the positive square root, like we are in this case, then that is the top half of this circle of radius 1, right? So careful with the limits on circle problems. We're going from 0 to 1 only, so that is just a quarter of this circle. It's just that piece. That integral means the area between this right here, this part of the circle, and the x-axis going from 0 to 1. So it's 1/4 of the total circle area. The total circle radius 1 would be pi r squared. If I need a quarter of that, that is equal to pi times, this is just pi right here, right? So pi divided by 4 is my answer. Okay, so I think we've done the box, the sum, the constant multiple. The add intervals, I kind of showed this to you already with the sine function, but it just means like if you are calculating the integral of a function from 0 to 10, you can also just go from 0 to 5 and then from 5 to 10. You can split up the a to b into here. Instead of going from 0 to 10, you can go first from 0 to 5, do that integral, and then add 5 to 10 to this integral. Okay. Let's do a couple of the other properties on the next page. Okay, this one, you can pause the video. It is already something we've talked about really, but you're going to use the sum to split up the integral, and then you're going to do it as shapes. So pause the video, and then I'm going to do the problem. So this one, first, practice writing your integrals out, and not just writing numbers. You want to get very comfortable with this symbol and writing this question like that. Now, breaking up the integral. Now you can go off and you can think on the side here that the first one is a line y equals x, and we're going from 0 to 1. So I'll have a triangle height 1, base 1. So that will come out to be 1/2. Plus, we just did the other one. It's just the circle again, right? It's a circle radius 1 again. And again, I have the top half of the circle. And then again, I'm going from 0 to 1. So it's this area, which we just said was pi over 4. If you put those two together, be careful to multiply here. 2 times 2. So it's 2 plus pi over 4 would be your answer. Okay, this b here is actually an example of the add intervals property, because look at this integral that we're given, 0 to 10. We're given that the integral from 0 to 10 of f of x dx is 17, which means the area under the graph of f of x, between the graph of f of x and the x-axis going from x equals 0 to x equals 10 is 17. This integral means the area between the graph of f and the x-axis going from 0 to 8 is 12. And you're asked to find this, the area between the graph of f and the x-axis going from 8 to 10. Okay, so I like to think of this like this. I write, you can say the integral from 0 to 10 of f of x dx is equal to the integral from 0 to 8 of f of x dx plus the integral from 8 to 10 of f of x dx, and this is my adding intervals property. And I can now put my numbers in. I know this one is 17, and I know this one is 12, and I'm trying to find this last one. And so this last one, the integral, just by math, right, subtract the 12, the integral from 8 to 10 must be 5. Okay. Now, if, let me give you another example using a similar problem. If I had told you that the integral, I'll do it in another color, the integral from 0 to 10 of f of x dx is 17, right? Say you were given that, and say that instead of saying the integral from 0 to 8 is 12, what if I had told you the integral from 8 to 0 of f of x dx is equal to 12? Find the integral from 8 to 10, okay? So then what we would say to ourselves is that we want to use this interval property. Integral from 0 to 10 is equal to integral from 0 to 8 plus integral from 8 to 10. That would be nice to use. However, I know this one is 17, but I don't really know the integral from 0 to 8. I know the integral from 8 to 0, right? Well, here's where the reverse property comes into play. the integral from, let me write it down here, the integral from 0 to 8 of f of x dx will be nothing other than negative the integral from 8 to 0, okay? So the idea is that now in our area calculations, we can go from left to right, from 0 to 8, but we can also go from right to left, right, from 8 to 0. We can kind of, if we have our graph, some of these integrals are as if we were going this way while we calculate our areas. So going backwards introduces a negative sign into the integral. So we just have to say here, if we know that going from 8 to 0, going backwards it was 12, then going forward from 0 to 8, it's going to be negative 12, right? And then if we're after this piece of the puzzle, then that is going to be equal to 29 for this particular problem, okay? Okay, so that's how we use the reverse property. Okay, one last property in the table is called the biggest box, smallest box property, and that is used to kind of put some bounds on an integral, right? So here's an integral. We know this is a number. Say I wanted to say this number is definitely less than some maximum number, and it's definitely more than some minimum number. Then how could I find these two numbers, right? So the way you could find it is you look at the integrand, which in this case is e to the negative x. So here it is. Here's 1, and the graph's going down here, e to the negative x, okay? So this is a decaying exponential. And say I were finding this area, right, from 0 to 1, 0 to 1. So now what I can say is the biggest box that I could draw around this area would be if I took the highest y value, and then I take the whole stretch that I'm doing my integral over, and I make a box, right? So the area of that biggest box is 1 times 1. And I get that by taking the highest y value on the interval, right? I can also take the lowest y value on the interval and make a box, right? And then I would get the minimum area that integral could be, right? So the minimum here would be e to the negative 1 is 1 over e. So this green box would have an area of 1 over e. So we can say that the exact area is somewhere in between. We know that the graph is neither constantly at the minimum nor constantly at the maximum. It's going between those, right? So that means that my area will be, the exact area will be between, let's see, it would be between 1 over e and 1. Okay, so that's a property of integrals also that we can sometimes use. Okay, you need to memorize these formulas. You're going to need to know how to find areas of triangles, rectangles, squares, trapezoids, circles, half circles, and quarter circles. With no formulas are not going to be given to you, so you need to know those by heart, which I'm sure you already do. And let's practice this last problem. So this last problem right here is, let's see what it is. We have a piecewise function, and you can see that you have lines and circles. So when you're looking for definite integrals under lines and circles, you are just going to be using geometry like we just did, right? So pause the video and see how many of these you can do by yourself before I show you the answers. Okay, so the integral from 0 to 7 will shade as we go. Is going to be the integral, the area right here, this green area, right? Just be careful, guys. These are easy problems, but it's easy also to make a mistake. It's 7 over here, etc. It's this trapezoid, right, has this trapezoid right here has a base of 7 and another base of 3. So this will be 1/2 of 3 plus 7, those are the two bases, times the height, which right here is 4. So this will be equal to 20. Okay, and let's just write that in here so that we know that this whole trapezoid was 20. Okay, then 0 to 13. 12 is here, so 13 must be here. Let's shade this trapezoid. Let's make it some other color like yellow down here, right? So my total from 0 to 13 is going to be 20, which is the first part, right? And then I'm going to be doing minus the area of this trapezoid right here. And so there I have the top base is 13 minus 7 or 6, and the bottom base is 11 minus 8 or 3, and the height is 3. So this is 9 times 3, 27 divided by 2, and so 13 divided by 2 is my net area going from 0 to 13, which is that integral. Going from -6 to 0, so this is still going left to right, and this is this circle here, right? This is going from -6 to 0 would be all of this half circle. Okay, so notice it is a half circle, right? So the diameter right here is 6, which means the radius is equal to 3, and I can do pi r squared, but I have to divide by 2 because it's just half of the circle, and I better have a negative sign on there because I'm going from left to right, but I'm under the x-axis. The graph is under the x-axis. Okay. Going from 3 to 3 means you're not going anywhere, and if you're not going anywhere, you're not gathering any area. So think of the integral as this thing that's accumulating area, right? Well, you didn't go anywhere, you didn't accumulate anything. If the bottom and the top numbers are the same, the integral is 0. Okay, integral from 7 to 0. Let's take a look at that. Now we're going from left to right. 7 to 0 is, right to left. Let me say that again. We're going from right to left, right? We're going backwards. So this is going to be minus the integral from 0 to 7, which we already calculated in part A or part 1, which was 20. So this is going to be minus 20. Okay, 10 to 4. So here we are going from, let's just check this out. We're going from here, 10 to here, 4, okay? So I'm going to need these two trapezoids, this one right here, which is under the axis, and this one right here, which is over the axis. I'm going from left to right, right? So let me just shade these. Okay, so this trapezoid on the bottom is 1/2 of 3, I think, plus 2 times 3, so that's 15 over 2. And this trapezoid here is 1/2 of 1 plus 3 times 4, which I believe is 8. Okay, so, but now, since I'm going from, in this problem, right to left, that those two trapezoids, the yellow one is going to be the positive one, so that's going to be 15 over 2, and the green one is going to be the negative one, right? So 15 over 2 minus 8 is going to be negative 1/2. Okay, this next one, we're going all the way from -8 to positive 13. I think that's all the way across the graph. So let's just add this last piece in here for this triangle. I think this triangle comes out to be 1/2 of 2 times 4, so that's going to be 4 for this guy. Okay, the circle came out to be 9 pi over 2, right? And then we had the green trapezoid 20, and the yellow trapezoid, the whole thing, the yellow whole thing was 27 over 2, I think, was this whole yellow trapezoid. Okay, so if I put all that together, I would have, starting at the left, 4 minus 9 pi over 2. I'm going from left to right, okay? And then plus 20, and then minus 27 over 2. Okay, and so I'd have 24 minus 27 over 2, which is 48 minus 27. I think that's 21 over 2 minus 9 pi over 2. 24 times 2, 48 minus 27. Yeah, I think this is right. I'm going to pause the video and double check. Yes, this is correct. You can also write it as 10.5 minus 4.5 pi. Okay, now a few goes from the past. F prime of negative 6 goes from the past will definitely keep recurring because it's a cumulative course, right? So F prime of negative 6 means what's the derivative? Remember that little word from last semester, the derivative at negative 6. Well, negative 6 is one of those places where the slope coming in from one side is different from the slope from the other side. It is also the edge of a circle, so for two reasons, this is going to be a DNE. The derivative doesn't exist, left and right are not equal slopes. Also, the right slope there was a vertical tangent line. Okay, F double prime of 6. Okay, 6 is here, so F double prime of 6 means we're on this line. F prime of 6 is some number, and so F double prime is going to be 0. F double prime of a line is 0. Average rate of change, 0 to 5. Average rate of change, or AROC, is the two y's. F of 5 minus F of 0 over the two x's. Rise over run. F of 5, I think, is 4 up here, right? 5, 4. F of 0 is 0. So this is going to be 4 minus 0 over 5 minus 0, or 4/5. What else? True or false? The integral from 0 to 2 plus the integral from 2 to 4 is equal to the integral from 0 to 4. This is true by our add intervals property. Okay, and then the last one. Over which values of x? It really should say at which values of x is f of x not differentiable. So we're looking for our sharp corners, our vertical tangent lines, and our, what else are we looking for? Any discontinuities is what we're looking for. So I think that we have places like that at x equals negative 6. We have a place like that at x equals 0. We have one at x equals 2. One at x equals, what is that, 5, I think? Yeah, 5. Another one at x equals 7. And I think, oh wow, another one at 8. Another one at 8. There's a lot. And another one at 11. Okay, so lots of sharp corners, a couple of vertical tangent lines also that are also sharp corners at negative 6 and 0. Okay, let's pause the video and try to do the takeaways and then see what I have to say about it. In words, the definite integral from x is equal to a to x is equal to b means, let's see, well, it means the area, but we need to be precise, right? So the definite integral means the area, or the net. Oops, what happened to that pen? It's way too thick. Okay, the net area. The net area between f and the x-axis from x is equal to a to x is equal to b. That's what that definite integral means. The definite integral from f of x from x is equal to a to x is equal to b is written as, well, it's the integral symbol, a on the bottom, b on the top, f of x dx. Don't forget to write the dx. For functions that are made up of lines and circles, right, like the one we just did in the last example, we can find a definite integral by simply adding up areas using the appropriate signs. And I would say, the big takeaway from this lesson is that when you see this, you know that you're dealing with an exact area. But if this area is a simple shape, if you can look on the graph and realize, oh, this is just this area, then we don't need a fancy limit or a Riemann sum or anything to calculate the area of a triangle, right, or of a circle. So it's more being able to recognize that the integral means area, and then just calculate that from geometry. That's the takeaway, okay? And the integral properties as well. So I hope you enjoyed that, and I will talk to you soon.